Okay, well, welcome back to the second lecture for the Deep NLP course. So today we've got Ed Greffenstedt here to talk to you all about lexical semantics. That's how to learn word meanings. So a brief sort of introduction of Ed. Ed's actually, I think he first came to Oxford as an MSc student a number of years ago, continued on to do a DPhil, a postdoc, and has ended up now in the language group at DeepMind. So he's a long friend of Oxford. So thank you, Ed. Take it away.
Okay, yeah, thanks for coming. So today's lecture, as Phil said, is about learning word representations that will be either independently useful or serve as input to a neural network, since this is, of course, about deep learning for NLP, and a frequent source of information about language is the vast swaths of text that we have on the internet and documents and emails, and we want to be able to apply models to that. Neural networks require continuous or at least vector representations as their inputs, so it stands to reason that we want some way of putting text in the form of words into these networks somehow. There won't be a lot of deep learning in this lecture, but we'll be exploring a few concepts that are prerequisites for understanding models studied in the rest of the course. So a little bit maybe about the sort of general history of this. So natural language text, in fact formal languages, are sequences of discrete symbols. We'll be talking about words as our basic unit, but obviously characters are a reasonable basic unit as well, morphemes, maybe phrases. But we'll be focusing on words today, and later in the course, Chris Dyer will talk a bit about learning representations at the subword level. So how do we represent words in a way that a neural network can take them as input, or in fact in a way that we can feed to any classifier of any flavor? Well, the most naive representation you could have for words, by the way, if anyone has questions at any point in the lecture, please feel free. This should be interactive, and there are no dumb questions. Well, there are, but so the most naive representation that you could possibly imagine is to simply encode your words as unique identifiers for that particular word type. So one hot vector, which is a vector where one element is 1 and everything else is 0, is a nice way of encoding unique types. If you want to encode all the words in your vocabulary in this way, you could simply have a vector space the size of your vocabulary, and each word would be a unique basis of that vector space, which would be obviously very large if you have a large vocabulary. This is a sort of naive method of encoding, but it's been used in a lot of classical information retrieval models. So for example, if you wanted to implement a simple information retrieval system, you might model documents as simply the superposition of the word vectors therein. So you just obtain a single vector of counts over each word, how many times a particular word occurs in that document. When you want to execute a query against your document base, you could encode the query as another document, saying it'll just put how many times each word in the query occurs and put that count into the vector. And then have some similarity metric over the vectors, for example, cosine similarity or inner product, and your most likely document or your most relevant document in this naive information retrieval system would be the one that most closely matches the query according to your similarity metric. And then you can rank based on similarity if you want to return k results. Similarly, this sort of naive approach has been used in basic word classification problems and topic models. In fact, topic modeling isn't a classification problem, ignore that, but it's been used in a variety of simple text processing approaches. There are obvious issues to this representation. First, if you're holding vectors for each of your words in a document in this kind of representation, you're having a lot of very large, very sparse vectors, which can have obvious computational issues to it. But from a more semantic perspective, you're treating each word as being a completely separate orthogonal entity to all the other words, right? The similarity between two words is guaranteed to be 0 if they're different words. And on top of that, they're very semantically weak representations, in that the vector for cat just tells you that it's this particular index in your vocabulary. It doesn't tell you anything about what a cat is and what a cat might relate to, and things about it being furry and cute and all these things. I like cats. So what do we want? We want richer representations for our words. When do we want them? Now. And we want these representations to be capable of doing several things, but as a starting point, it would be nice if they could express semantic similarity. Tell us at least that cats and kittens are close to each other as concepts. They're perhaps a little less, they're perhaps mutually less close to the concept of dog, but that these three concepts cluster more closely than cat and steamroller, for example, unless you have a very peculiar interpretation of these concepts. One sort of dictum you'll hear, or quote you'll hear a lot in the context of learning representations that have these properties is this quote by J.R. Firth, "You shall know a word by the company it keeps." There are many other thinkers in philosophy of language and linguistics that have said similar things, notably Ludwig Wittgenstein, who said around the 50s as well that that meaning is simply use, that we understand language by understanding how it's used in a particular community. And we'll talk today about how you can translate this idea into a method or several methods for learning word representations. So we're going to be producing dense vector representations as opposed to these very sparse vector representations based on the context and use of words. There are three main approaches that we'll be covering in this lecture, but some of the concepts will be revisited throughout the following lectures. The first one we'll see is a count-based method, which is definitely of a very different flavor than the more neural network-inspired approaches we'll see in the rest of the course in the later part of the lecture, but is a nice starting point to gain intuitions about what we mean by learning word representations based on context. We'll see a predictive approach where we're going to learn word representations by predicting the context or by having the context predict a word. And finally, we'll talk a bit about task-based or extrinsic approaches to learning word representations, where the representations are learned by how well we optimize word representations based on how well they help us perform a particular task. Any questions before I launch into this? What's a vector? I heard that over there. Okay. Okay, so count-based methods. So these have been around for several decades, and it's still a nice, popular, and cheap way of constructing word representations. So there are several parts to this, and in general terms, the procedure is thus. We're going to start by choosing a basis context vocabulary of context words. So this is a set of words in our vocabulary that we choose based on our linguistic intuition or statistics of the corpus. We want these context words to be informative about meaning. So we might not want to include in this set common words like the, some, because these are function words. They don't really tell us things about content, at least in this particular approach. You might want to also ignore really very rare words. So a common procedure is to take the top K words in your vocabulary, like 1,000 or 10,000, which seems pretty large, and exclude function words from a stop word list that you might obtain from your favorite linguistics website. So we define this basis vocabulary as a sort of hyperparameter to our model. And then we're going to have to select a notion of what context is. So there are many complex ways of picking context, but one simple approach, which is surprisingly effective, is to simply say that the context to a particular word is a window of words surrounding it. So W words on either side of the target word that you're learning a representation for. Obviously, you could do clever things here too. You might want to remove from the window words that don't have like a dependency relation, that aren't syntactically related, but we're going to keep it simple initially. And once we've defined both of these things, we are going to, for each word we want to build a representation for, count the basis vocabulary words that occur on the left and the right window of each instance of our target word, and simply collect those counts in a vector. So here's a little example on how we can learn representations for the concepts or the words cat, kitten, and dog. So we have a mini corpus up here, where I've already sort of pruned out the everything that wasn't 3 words to the left or 3 words to the right. And we're going to use as a basis vocabulary, which I pulled out of nowhere, the words bit, cute, furry, loud, meowed, heard, ran, small. And again, when you're picking context words, you might want to do clever things like normalize by case. You might want to run a stemmer so that you don't have all that ran, run, running are all the same context word. But again, these are just details of the model. So we look at our corpus and we want to learn vectors for kitten, cat, and cute. So we collect the words that are in their context and are also part of our basis vocabulary. So we ignore words like and the, which aren't part of the basis vocabulary. And we simply collect a set of the words that occur in the context in our corpus. And then since each of these, conveniently enough for this example, occurs once, we can then translate it into a vector of counts, which in this case looks binary, but obviously these could be 2, 3, 4 if we had a larger corpus, and where each position is indicated in the order I presented the basis set in. So here we have now a vector for kitten, for cat, and dog that are no longer one-hot, which are no longer completely sparse. So then, if you have these vectors, you can do simple things like compare the similarity of concepts according to the corpus you've looked at. So you could use inner product, for example, or cosine measure as a similarity kernel, and simply calculate the similarity between your concepts. So here we find that kitten and cat, which, just to remind you, are both furry, both purr, both meow. So kitten and cat are quite similar according to this metric, 0.58. In contrast, cat and dog are a lot less similar, and kitten and dog are completely different. So we get this idea that things that are similar according to what context they appear in cluster in our vector space. For these kind of count-based models, the cosine measure is one of the popular sort of similarity metrics that you'll find a lot in the literature, primarily because it's norm invariant. You're normalizing the vectors by their norm, by their length, and then you take the inner product of the unit vectors. So that if you had a word that occurred a lot in the corpus and a word that occurred just a few times, you're just checking that they point in the same direction rather than that they point to the same area of your space. So this is a pretty naive approach, and I mean, we get this nice intuition from this example, but it's a pretty naive approach because we're not really capturing some aspects of these collocational statistics that we might want to capture if we just count. Not all words are equally informative. Some words might occur a lot. So if you have a corpus about animals and you want to distinguish the concepts of various animals in this corpus, the fact that they all run and have like 4 or 2 legs, etc. Some of these words are just going to occur in the context of all these concepts and not really tell something about whether or not they're similar or different because they're just very frequent words. So there are many statistically motivated vector normalization methods, which I won't go into detail because this is more of an introduction to this concept. But for example, you could normalize the counts by taking the term frequency over the inverse document frequency, which is a common normalization method used in information retrieval. You could take point-wise mutual information, etc. There are a bunch of survey articles that cover these things by, for example, James Curran in his thesis, or by Marco Baroni's group. Which you can ask me about if you really care about the more historical methods. Some of these normalization methods remove the need for norm invariant similarity metrics, or actually induce vector representations that are distributions over context, so you can use slightly more statistically motivated similarity metrics, like taking the KLD, the Kullback-Leibler divergence of the 2 distributions as a similarity metric. But perhaps there are easier ways of addressing this problem of what are salient features and what are not, what context words help you learn the meaning of a particular word and differentiate from others or project into the same space if they are similar, without having to make these sort of high-level decisions about your context windows, about your basis vocabulary. So the first way of moving away from just this simple count-based method are these neural embedding models that you might have heard about. The very popular one is Word2Vec, and we'll talk about that a bit today. What am I doing for time? But before I jump into those, let's think about what we've just built in the previous example. So we've collected counts and produced a vector for each of our vocabulary words, of our target words. You can think of this collection of vectors as forming a matrix. So the rows of the matrix, or depending on your convention, the columns, are the words of your vocabulary you're learning representations for, and the columns of the matrix are the basis words, or the features that you've used to represent the meaning of these words. If we want to think from a linear algebraic standpoint about how we would use this matrix as an operation, we can represent the symbols in our vocabulary using our initial naive picture of like saying every word in our vocabulary is a one hot vector, and the representation is retrieved by multiplying that one hot vector by this embedding matrix, which simply retrieves the corresponding row. And this notion of embedding matrix is what is going to persist throughout this course as like sort of the entry point into neural networks, when we're going to translate words from discrete symbols into dense representations. But we're going to see how we learn it in a way that's different than just counting. The generic, or at least one generic idea behind embedding learning, so instead of estimating this matrix through counts, actually learning it directly based on some task, is that we're going to tune this matrix in order to maximize some score across a corpus. The generic algorithm will explore various instances of, in the form of the Colibra and Weston embeddings and word-to-vec models, is that you are going to learn a particular row of the matrix. You're going to collect all the instances of the word that row corresponds to. For each instance, we're going to collect its context words according to, for example, the window-based method or some other heuristic. And we're going to define some scoring function over that instance and its context that has as free parameters some parameters theta, which might be, for example, well, we'll see some examples, and the embedding matrix with an upper bound on the output. And then using that, we're going to define a loss that we're going to try and minimize across the corpus and all the words in the corpus that is going to try and maximize, or it's going to try and maximize the score by minimizing its negative. In minimizing this loss, we're going to try and estimate optimal sets of parameters in an optimal embedding matrix that minimizes it. Sorry, that's circle. And then finally use this estimated embedding matrix as the input to our network, the transform input to our network. So the design of the scoring function matters deeply. It's very easy to design a useless score. So for example, if you could define, if you just read that previous slide and say, I'm just going to define a scoring function that's going to constantly output my upper bound, that's cool, you're going to satisfy the objective, but you're not going to learn a useful embedding matrix. So a leitmotif throughout the next few models we're going to study is exactly why the scoring functions that they implicitly define is useful. Ideally, your scorer is going to have to obviously use the embedding matrix that you're optimizing to embed T and produce a representation for it. And the score that it produces should be interpretable, ideally, as a function of how well that particular instance of the word is accounted for by its context or vice versa. So how well it reflects its use in a corpus of natural language. More so than, for example, if you replaced it with a random word from your vocabulary. And finally, because we're going to be estimating these representations using backpropagation or gradient descent, it'd be nice if the loss was differentiable with regard to the parameters of the model. So a first and popular, this is not historically the first, but a popular approach to producing embeddings as present in this paper by Colibra and his colleagues in 2011, Natural Language from Scratch, or something to that effect. I can't remember the exact title. And the idea, and it's a fairly simple idea that sort of ticks all the boxes we saw in the previous two slides. We're going to take as context all the words in a sentence, and we're going to jointly learn their representations. So we're going to pass each word in the sentence through the embedding matrix, which is perhaps randomly initialized, and get an initial proposed vector for each of those words. We're going to pass that through a shallow convolution, so this could just be adding them together if you wanted to take the simplest approach, but you could also define a simple convolutional network, which you'll probably see further in the course or have seen in your introduction to machine learning. Have they? Phil? Have you seen convolutional networks in your introduction to machine learning? Okay, cool. So you could pass it through a convolutional neural network, simply add them together. And the aim is you're going to produce a single representation for your sentence. And then you're going to pass that through a scoring function, which just projects that vector into a scalar value. So you can think of all the green bits there as being parameterized by the other parameters of your model theta, and the vectors at the bottom are produced by putting your one-hot vectors through E, which is what we're trying to learn here. So the overall network models a function over sentences, G of theta and E, which is produced by putting the embeddings of the sentence through the score. So this is everyone satisfied that this implements a scoring function? Right. So there's a trivial sort of solution if you think, okay, I just want to maximize the score at the top of this through gradient descent. There's a trivial way in which this model could produce a degenerate solution, which is it could ignore the inputs and just constantly have a strong bias on the final projection that says I want to output a score of 1, for example, if that was our upper bound. So in which way can we prevent this network from ignoring its input and learn good representations by forcing the score to be conditioned on the representations? Well, the solution that Cullenberg and Weston proposed is to, during training, every time you observe a sentence, you're going to sample a distractor sentence simply by corrupting one or more words of that sentence. So how many words you corrupt is up to you. It's a hyperparameter of the model. But you can think that a simplest case would be you randomly select a word in the sentence and then randomly sample another word from the vocabulary to put it in. So if you had the cat slept and you change that and you have the car slept, that's the distractor sentence. And we're going to present both sentences to the scoring function, and our loss is going to be a hinge loss. So it's going to be 1 minus the difference between those scores. And if that goes below 0, you ignore it. So you can think of this as saying it's fine if you ignore the input to the scorer and just output a constant function. Trivially, you're also going to output a high score to sentences which are garbage, which you've just put some random words into. So the optimal solution for this model is to have to actually rely on the information within the representations of the word in order to produce a good score. Are there any questions about this? Yes.
So what is your training data in this session?
Oh, yes. So that's an excellent question. So I didn't go into that sort of detail, but typically, whether you're estimating counts or you're estimating your embedding matrix by using, for example, the Cullenberg and Weston model, you typically want to use a large corpus so that you can have sufficient use of each word to learn a good representation. But you might want to also think about what you're going to be using the vectors for. So language is used differently across different domains. If you are using if you're using words to talk about politics, you might use a different vocabulary and different meanings of words because natural language can be ambiguous or polysemous than if you were talking about video games or about computers. I need to come up with richer examples. So it's good to think about training your word embeddings on the same sort of domain, same sort of vocabulary as what you're going to be using them for. If you have sufficient data, so if you had enough time, enough computers, and you could just take all the Wall Street Journal and all the internet, then you could produce perhaps general purpose embeddings. But in practice, that's not computationally feasible, especially with the sort of computers we have here. And you simply take a corpus that's sufficiently large about your target domain.
But what is the correct score in this setup?
So the score, that's more of an implementation detail, but for example, you could bound the score at the top by saying that there's a maximum. So you put the projection into the scalar through, let's say, a sigmoid. So it's the score between 0 and 1. There's no objective notion of the score. You're basically, there's no real objective notion of the score. You're just trying to maximize the score. And the purpose of the distractor sentences is to force you to not give good scores to sentences which don't belong from your corpus. Sorry, that's perhaps a little unclear. So so let's revisit this. the scoring function is being applied to a sentence which belongs in your corpus, and a corrupted sentence which doesn't belong in your corpus, because you've just taken a sentence from your corpus and replaced random words. In a sense, you don't need to really think about this as providing an objective evaluation of the quality of an English sentence. It's basically a discriminator between whether or not the sentence it observes belongs in the corpus or doesn't. This objective function penalizes you for also giving high scores to sentences which don't belong in your corpus, and rewards you for producing sentences which do belong in your corpus by forcing you to try and maximize this difference. Is that right? Yes. So, and the interpretation of this this kind of approach is that the representations you learn by optimizing, by minimizing the loss, are representations which carry information about what the neighboring representations should look like in your sentence. So if the neighboring representations are something that express information that typically you would find grouped in the corpus, then it should give it a high score. And if the representations provide information about something which doesn't look like it belongs there, like for example, part of the sentence is about cats and the other part of the sentence is about computers. Actually, those are pretty frequently associated on the internet. Cats and medical operations, then your representation should be sufficiently different to indicate to the scoring function that there's something wrong and that the score should be low. So this forces word representations to somehow encode information not just about the words, about the symbol itself, but about where it belongs. Does that make sense? That's quite hand-wavy, but that's most machine learning for you. And this sounds a lot like the distributional hypothesis we saw at the beginning. We are trying to learn representations that contain information about their context, about the company. You're learning a word by looking at the company it keeps. So this first stage of the model is fairly sensible, but it's deep in that you have a convolutional neural network. You can have some nonlinearities. The score typically is a multi-layer perceptron. It sounds a lot more complicated than it should be, and the convolutions capture very local information because typically they're looking at the neighboring few words, because the sentences can have variable length. A slightly more popular approach that is still frequently used today is word-to-vec that was introduced by Mikolov and his colleagues in 2013. And there are two variants to this model. The first one is called contextual bag of words, and then the other is called skipgram, and I'll describe these both now. The idea behind this is that instead of having a scoring function, which, as you pointed out in your question, is kind of strange as a concept, because what is the score of a sentence? Why should we have some sort of an uninterpretable score there? Is to literally have the context predict the word. So we think of the K words on the left and on the right of your target word, and good embeddings of that context should, when fed into this model, be able to predict the word that's missing in the center, or have a distribution that's peaky around that particular word. So how this works is we're going to look at our context words, pass them through an embedding matrix, which we're jointly training, and we're going to simply add them together. We're going to have a linear layer that's parameterized by the vocabulary size, and use that to project that hidden layer in the center that we've obtained from adding the word vectors back into the size of the vocabulary. So perhaps poorly represented on this diagram, but that top vector should be the number of words in your vocabulary. And then you're going to pass it through a softmax, which I've reminded you what that looks like mathematically here, in order to get a distribution over the vocabulary. So we can think of that last vector as outputting, or as representing, a distribution over what the target word should be given the context of that target word, given the observed context. The mathematical, nope, that's the wrong thing, sorry. The mathematical representation is fairly simple, as you're going to put your one-hot embeddings of the context of each context word through the embedding matrix and then project it. So because these are both matrices and there's no nonlinearity, you can see this as actually just one big matrix. But as an efficiency trick, you can actually move that projection matrix outside of the sum in order that you just take this, you're literally just taking the sum of the embeddings and only doing one matrix multiplication rather than k, if you have k context words. We're going to train both the parameters of the projection, which are only there to predict the distributions, jointly with the embedding matrix, which produce the embeddings of the context words, simply by minimizing the negative log likelihood of the data. So simply by iterating over each word in the data, and for each one calculating the log probability of that word given its context according to the model, summing through that, and then minimizing the subjective, which you can do through backpropagation if you have an autodiff library. Well, there's not much need for backpropagation in just matrix multiplication. So the advantages of this model, in contrast with the Cullibert and Weston model that we saw previously, is that everything is linear, is very fast, and it's basically a very cheap way of applying one matrix to all inputs, but we split it into two matrices and get some efficiency out of summing the embeddings rather than doing that expensive projection matrix a few times. Historically, this model was trained by doing negative sampling instead of doing the expensive softmax, although computers have gone significantly faster since 2013, and we have good implementations of softmax, of the softmax operation in a variety of libraries. So you get, it turns out that just doing negative log likelihood minimization is better. It's more stable and it's fast enough. And there are several variants that you could imagine to this model. So if we look at the maths, okay, we need to put this somewhere else. If we look at the maths in the previous slide, we have a single projection matrix per word. But you could imagine saying, okay, that's not very rich. It's cheap because we can move it out of the sum. But a word that's one word to the left of our target word might be providing different information than a word that's two words to the left. Likewise, if you had the syntactic information, if you had a parse of the sentence, you might imagine that a verb is giving you different information about one of its arguments than, for example, an adjective might. So you could actually untie this. You could have a matrix that's actually dependent on either the position or the nature of the syntactic relation between the words. One of the variants which I quite liked is Ling et al. 2015, where they simply have position-specific matrix per input. It's more expensive, but it gives you a richer kind of representation. Another variant on this is the skipgram model, which is also under the word2vec sort of header. And this is sort of turning the previous model on its head, where the target word is predicting the context words. So the idea here is that you're going to embed the target word with your embedding matrix, which again you're jointly training, and you're going to project that straight into the vocabulary and put it through a softmax. So that's giving you a distribution over other words in the vocabulary given that word. And we're going to learn to estimate the likelihood of all the context words. So the likelihood of a set of context words given the middle word, your target word, separates out into, the log likelihood, negative log likelihood, separates out into the log product of the probabilities of your context words given your target word, and you can move the log through there and have negative sum of the log probability of each target word, each context word given the target. So this is very fast. You only have one embedding operation versus k, or size of your context. And you can just read the probabilities off from the softmax at the end. And here there are similar variants to contextual bag of words that are possible. You could have position-specific projections, and obviously you're trading off between efficiency and a more structured notion of context if you do that, but you can learn richer representations through that. But one of the things that appeals to people because of that, if you don't do that, is just the relative simplicity of this model. It's easy to implement. There are a bunch of reference implementations in TensorFlow and Keras and Dynet probably that you can look at. Yes?
Quick question. Going back to the previous slide, so the initial point of the exercise was to get an embedding, so like a reduced representation of your words. So with the skip gram, don't you lose that because you're ultimately doing a softmax on the entire word?
Yes. So is a good question. So this transformation plus your softmax is the theta in your model. These are just something that allows you to model that distribution given the representation. The embedding matrix, which again I probably should have shown explicitly, is what allows you to obtain this dense vector here. So you obtain that by putting your one hot of your target word through the embedding matrix, and then you project into the vocabulary. So in a sense, these models, both the Colobert-Weston and both of the word-to-vec models, have parameters that we don't really care about. I mean, we're not going to reuse them. Their only purpose is to produce the scoring function. And through that, allow us to model an objective which forces the overall model to learn a good representation. So that if the representations aren't rich, if they don't contain information about their context, you won't be able to predict the context word given the target word. You won't be able to produce a good score in the Colbert-Weston case. And that's kind of the point of the exercise. Does this make sense? Okay. So to quickly compare these people often refer to word-to-vec as deep learning, but it's not. It's a completely shallow model. That's what's nice about it, is it's fast. But it has this sort of like neural flavor because we have a projection matrix. We implement them in the same libraries that we implement neural networks in. You can use backprop if you're really lazy, but there are other ways of training them. But these, when you compare them to count-based models, they actually are embodying the same sort of idea. We're trying to exploit the statistics of our data set, the sort of regularity with which words co-occur in order to derive representations. And in fact, it goes deeper than just this high-level similarity. In 2014, Omer Levy and Yev Goldberg produced a really nice paper showing that word-to-vec as a model, I think it was Skip Graham rather than contextual bag of words, is actually equivalent to learning the PMI matrix factorization of count-based models, which is one of the normalization methods of normalizing count-based models, which I discussed but didn't discuss in detail. And if you care exactly about the detail of this theoretical result, then I invite you to read the paper. Following that publication, which showed that effectively you weren't only just doing the same thing on a high level, but you're actually doing the same thing mathematically, Omer Levy and colleagues produced a follow-up paper where they compared PMI matrix factorization, word-to-vec, Colbert-Weston, and some other slightly more involved embeddings learning methods, which I won't cover in this lecture, and showed that if you had all the hyperparameters for each of these methods and you optimize them correctly by grid searching or by brute force, then they have roughly equivalent performance. They're not really distinguishable. This isn't to say this isn't an interesting area of research, but there were a lot of papers that made pretty strong claims about how they had a new, better, global way of producing word representations, and it turns out that if you tune them just the right way, they're hard to distinguish. This isn't to say that some aren't easier to train than others, which is important. So the benefits of these neural approaches are that they're easy to learn. With good linear algebra libraries, and in particular with auto-differentiation libraries like DyNet or TensorFlow, it's very simple to implement these in a few lines of code. And again, there are reference implementations for most of these online. Especially with regard to models like the word-to-vec models, they're highly parallelizable. With mini batching, with GPUs, with distributed models, you can train these very quickly across a large amount of data. What's nice with both count-based and with neural models is you don't have to predict just other words. You could imagine variants where you're predicting other aspects of context. These might be discrete, so you might be predicting what sort of dependencies you observe in the context. If you had data that was dependency parsed, you could predict pause tags, you can predict anything like that. And while you can estimate these probabilities with counts, it can quickly become hard due to sparsity. But the appeal of these, of the objective-based methods like word-to-vec, where you're predicting the likelihood of the context, is you can also do this over continuous context. So for example, if you had data that paired sentences with images, you could predict pixels, the probability of pixels given your sentence, and somehow put the information of the image in the word. Is it that simple? Not really, but I mean, it opens the door to these kind of richer notions of context that are definitely harder to address with count-based methods. So how do we evaluate these word representations? Well, there's a bunch of data sets. Some are good and some not so good. First, there's WordSim 353, which is just, actually I can't remember the details of it. It's a set of pairs of words, and you have have human reference scores, and you have to see how well your model similarity scores align with those. It's been around for a while, since 2003, and there have been so many papers published on it that the sort of research community has collectively hill climbed over this data set, and it's still a good sanity check, but it's not necessarily the best way of evaluating word vectors. SimLex 999 is a similar kind of word similarity sort of data set that you can use to evaluate your representations. It was published in 2016 by Hill and al. It's been around since 2014, but that's kind of the same flavor as WordSim 353. In the Word to Vec paper, Thomas Mikolov presents this word analogy task where you have like x's to y, like y's to z. And he showed that you could solve these analogy problems simply by using vector arithmetic. So there's this famous example that you hear people refer to all the time within the context of Word to Vec, which is that the vector for queen can be obtained by subtracting the vector for king from man and adding the vector, no, this is the wrong way around, sorry, I've copied this from a website. The vector for queen can be obtained by subtracting the vector for man from the vector for king and adding the vector for woman. So you're basically saying, take a king, remove the information that identifies the male gender. This is in a very hand-wavy sense. We're not making a deep statement about kings and queens here, but more about the statistics of these words. And add the information about women, and you should obtain a vector that is close in the vector space, where this nearest neighbor is the vector for queen. Yes?
What are your thoughts on why statistics cause that property to happen?
I'm guessing, I mean, so from more indirect observation and that other people have run experiments on this, you find that words that are very frequent, so that are ahead of the Zipfian distribution, you find this behavior is quite robust, and then for rarer words, it doesn't occur as much. You don't necessarily have a robust performance. One interpretation could be that if you remove basically the contextual information, you're removing from the vector king the contextual information that identifies the man by subtracting the man vector, and then you're re-adding the contextual information that sort of predicts woman, or that woman predicts, and that is sort of equivalent in a sort of it's equivalent to like the contextual information that queen predicts. That's very hand wavy, but yeah, that's the best explanation I can probably muster up. Yes. This is a nice sort of, it's more than just taking pairwise similarities between words and actually doing a sort of simple reasoning task, although it's a very superficial one, but it's quite popular to evaluate word representations these days. And finally, you can get a qualitative evaluation of your vectors by simply using a projection algorithm. So a popular way of projecting these high-dimensional vectors, even though they're dense embeddings, you're no longer talking about 10,000 dimensional vectors or vectors the size of your vocabulary, but you project them into a smaller space, the size of which you can control as a hyperparameter. There's still more than 3 dimensions, so it's difficult to picture anything beyond 3 dimensions. Or on a sheet of paper, it's difficult to portray even that. So there are algorithms like t-SNE, which allow you to project high-dimensional spaces into 2-dimensional spaces and then observe how words cluster. And I stole this from Chris Ola's blog post, which is fantastic, actually. You can just read this blog post and you'll get most of the contents of this lecture, I think. And you see that if you project things that numbers occupy a particular part of the space that's closer than other words, that words like minister, leader, president, that you just, representations that you produce from, I can't remember what the corpus was, but if you looked at a large collection of web pages, you would plausibly find that words like president, leader, minister are close together. This would be a good time for a witty political comment, but I don't have any. So this sort of qualitative evaluation should be taken with a grain of salt. T-SNE is something where there's some aspect of randomness to it. If you hit refresh or like regenerate your projections, you typically will land with one that looks kind of good and that you can overinterpret, and that's what people do in papers sometimes. But if you're training a model and you want intuitions about what your representations are expressing, it's still nice to observe that, hey, sometimes if I hit T-SNE, if I run T-SNE enough, they actually do cluster in a way that is matching my intuitions, and you can therefore introspect into your high-dimensional representations without having to read out the numbers directly. So these are this collection of evaluations are something you could call intrinsic evaluations. They're evaluating whether the words themselves cluster in sensible ways or have particular geometric relations in the case of the analogy tasks. But you're evaluating the words, those representations kind of in isolation or pairwise. And it's an intrinsic kind of evaluation. Another way of evaluating the representations you learn with this would simply to be as we'll see in the rest of the course, we have different sort of architectures we can feed these into to generate other sentences or classify them or predict some aspect of a document. And an extrinsic evaluation is simply, do the embeddings that you trained help you perform this end task better? Are they good general purpose representations? And we'll talk about this a little bit later in this lecture, but also this will be part of the content of the rest of the course. Yes?
If you go back to the just wondering, is that team subject or subject?
Yeah, as I pointed out, I copied this from this web page, and I think they made a mistake here. So this should be king minus man plus woman equals queen. I'm pretty sure. I'm going to double check this in the original paper and fix the slide. Okay, so we've seen the sort of general intuition behind learning vectors by counting context words. We've seen a sort of more neural network inspired approach for estimating them based on maximizing scores or likelihoods. And finally, I want to talk a little bit to wrap up this lecture about task-based embedding learning. One use for this embedding matrix, following upon my comments for extrinsic evaluation, is to treat the embeddings as input features to a neural network over words. So we want to not just use these word representations to compare or cluster words, but we want to use them as input to functions over continuous representations and do something with it: predict, classify, generate. If you think about this input process, this input operation is just another matrix multiplication, of which we might have many in a neural network. So in a sense, the embedding matrix itself is just another parameter in your overall neural network. Since we update neural network parameters by doing gradient descent over, by taking the gradient of the parameter of the loss with regard to the parameters and updating the previous state of the parameters, we can just do this to the embedding matrix based on our task-specific loss. So if I'm, let's say, predicting labels y from inputs x based on the parameters of my network, if I optimize the parameters of my network, I might as well just optimize everything else, including my embeddings. So you can think of a sensible approach might be simply directly train the embeddings jointly with the other parameters of the network which uses them. And the general intuition behind this is that we are not only learning to predict or classify or generate based on these embeddings as features, but we're jointly learning the features themselves. We're trying to find out what the salient features are for my task. This embeddings matrix that we use as just another set of parameters in the network could be learned from scratch. So we could just randomly initialize it and just learn it based on the task. Or we could initialize it with embeddings we learned from some other source like Word2Vec over another corpus. Especially if we have a lot more data that is unlabeled. We could just simply train a Word2Vec model on that and use the embeddings matrix to initialize the embedding matrix of our task-specific model. So this is often referred to as fine-tuning. I'll give you a few examples of this to wrap up. So for example, so we're going to talk about bag of words classifiers because we're going to talk about slightly more involved models later in the course. So we'll keep it simple here. We want to classify sentences or documents that have a variable number of words in them into a particular set of classes. For example, whether or not a tweet is a positive sentiment or expresses a negative sentiment about a politician, or whether or not a movie review is 1 star, 2 star, 3 to 5 star, or perhaps we have a finite set of topics or document classes, and we want to predict which of these classes an email belongs to, whether it's about computers or about religion. So the simplest approach to classifying is a bag of vectors approach. Simply, we're going to embed all the words in our document with our embedding matrix, and we're going to sum them. So we're not taking into account word order or any sort of compositional relationships between them. And we're going to project that into our classes. Once we've projected, we want to yield a probability distribution over the classes, so we'll simply softmax. And this, you can have a simple kind of like linear model like this, where you simply embed and then have a simple transformation. You could make it arbitrarily complex, obviously, by having a convolutional neural network over the inputs or a multi-layer perceptron, and it's really up to you. But the same approach is universal across all these things. We embed first, then we pass it through a bunch of transformations into our classes. This kind of bag of vector classifier is fairly simple to implement and train. I gave you a few example tasks earlier: sentiment analysis, document classification, author identification. Whatever you have data for, you can do this for. And by training or fine-tuning our embeddings based on the end task, you can think of the embeddings encompassing or internalizing task-specific features. If your end task is classifying the sentiment of a tweet, you can think about individual word representations, internalizing whether or not that's a word that is indicative of positive sentiment or negative sentiment. So the word meaning in this kind of context is grounded by the task, grounded in the task. The task gives it meaning. But this doesn't really give you, this kind of approach doesn't give you any notion of words in context. We're just summing them together and then classifying. And that seems pretty weak because in language, typically words gather meaning by existing in a context. That's how we resolve ambiguity or the polysemy, and we determine which particular meaning of a word is salient in a particular context. Also, everything in this kind of simple approach, every word in the document contributes to the end product, to the classification. So if you have more words, then you have the risk of incorporating more noise into your model. Finally, grounding, this way of learning word representations by grounding them in classification tasks could yield quite shallow semantics. I mean, obviously, it's good that your word representations would internalize the notion of positive or negative sentiment in sentiment classification, but there's obviously more to the meaning of the word good than whether or not it expresses a positive or a negative sentiment. There's more to the word CPU than the fact that it's a reliable predictor of the topic computer if you were doing document classification. So another approach to, and this is the final approach we're discussing in this lecture, another approach to learning in a task-specific setting fairly general word representations is to form an objective where you need to learn something where the objective reflects something linguistically general. And one example of a fairly simple objective that does this is a paper by Herman and Blensom in 2014, where the task is recognizing whether or not two sentences, one in German and one in English, express the same meaning. So whether or not they're aligned in a corpus or not. We're not talking about word-specific alignment. We're just saying whether or not these two sentences are roughly a translation of another. So consider a data set of English sentences and their German translations. So we have everything's paired and we assume that the data set has the English sentence is roughly the same meaning as the German sentence it's paired with. And we want to produce representations of the vector representations of the English and the German sentence such that the similarity between these vectors is maximized. We're going to use a simple objective of maximizing the similarity to train embedding matrices for the English and the German sentence, for the words of the English sentence and the words of the German sentence, and then we can use these embedding matrices for whatever task we want later on. And I'll talk a bit about why this is a nice general purpose objective. There are a bunch of different ways you could compose the word vectors to produce a representation of the sentence. And throughout the course, you'll see some very sophisticated ones. We're using recurrent neural networks, convolutional neural networks. But we'll talk about the simplest composition functions that we use in the paper. Obviously, you could just add them. Or you could try and capture some aspect of word order. So for example, you could take collocated pairs of words, so a word and its next word, and just put a nonlinearity on that. So you're no longer just taking a sum of all the words in the sentence, but you have a moving window over the sentence, and you're applying a nonlinearity to each pair of words. This is a fairly trivial way of capturing some notion of word order. As I said, it's not the most sophisticated thing you could do. So we have simple ways of producing a representation for the English sentence from its words or the German sentence from its words. Obviously, this should be in the embedding of TI and the embedding of TJ, and of TJ plus 1. So an obvious loss would be simply to minimize the difference between the distance between the English vector and the German vector. So if when you compose the word representations, you obtain the same vector, the norm of this overall difference vector goes towards 0. Let me take the squared norm. But this has an obvious degenerate solution. So if the objective is to minimize this loss, the simplest solution would be for the model to simply learn that every word has the representation 0. So that when you add them together or do the slightly more complex composition function, you trivially minimize this loss. And this is, again, going back to what we talked about in the Colburn-Weston method, where we're predicting a score. It's important to think about what these degenerate solutions might be, and we want to ensure that the objective is designed such that the only way to minimize the objective is for you to learn meaningful representations. So you can avoid the degenerate solution with a similar approach to the Colburn-Weston objective. So we're going to do a noise contrasted margin-based loss, which is a bit like a hinge loss. And we're going to basically take for each pair of sentences, English and German I, we're going to sample another German sentence from the corpus, a different German sentence from the corpus, which is now a distractor. And we want to maximize the difference between this distance and this distance such that it's more than m. So if you would think about it this way, if you have the degenerate solution and everything's mapped to 0, this will be the norm here will be 0, the norm here will be 0, and then you'll have this margin that stays. So you won't have minimized your overall loss. What you want to do instead is ensure that the similarity, the distance between your distractor and the English sentence representation and the English and the German sentence representation is at least your margin. M here is just a hyperparameter, so if you increase the margin, you're saying that the model needs to be increasingly discriminatory about distractor sentences, and if you make it smaller, it doesn't matter as much. So the intuition behind what happens when you minimize your loss here is that aligned sentences between English and German share the same high-level meaning if one is a translation of the other, if they have the same meaning to us humans. So to minimize this objective loss, the embeddings have to be able to accurately, or at least somewhat, reflect the high-level meaning of the sentence in which they occur in order to minimize the loss, while also modeling their context. So this is a nice example of a task-based objective, which is simple, fairly simple to implement. But unlike doing sentiment analysis or document classification, you're learning a fairly general notion of word embedding. You're using another language as a sort of grounding for English representations and vice versa. So these models are very simple. There are many other options. Sorry, how much time do you have left? A little over time. I'll wrap up. So these models are all very simple, and that's not a bad thing. I mean, it's easy to think about overly complicated ways of learning embeddings, but ultimately, very simple approaches are easy to train and have been shown to be fairly robust. So it's not necessarily good to just immediately jump to something more complex. But it doesn't really address all the aspects of language that we'd want to capture. when all these models for classification and even for detecting similarity between English and German sentences don't really do anything in terms of capturing the relation between words, about the like disambiguating words, looking at the context and how they would affect selecting the meaning of a particular word. So, oh my, I forgot to finish this slide. This is what we're going to be discussing in the rest of the course. How can we use these embeddings as the input to more complex neural architectures and in order to solve more complex tasks? So to wrap up, task-based embeddings are nice because they capture information salient to the task, but this doesn't guarantee that you're going to learn general meaning. You're going to learn only the meaning or only the sort of representational information that is useful for that particular task. You could overcome this by using a multitask objective, but for using the same representations to classify documents, to predict sentiment, but that has its own difficulties. Yeah, let me just wrap up here actually. Yeah, sorry. So what I'd like to finish, on is how these vectors will be used in other parts of the course. You can think of learning and reusing word vectors. So if you pre-train them or if you learn them on tasks as a form of transfer learning, you're transferring information from the objective that you use to train them. So in Word2Vec, predicting the context or having the context predict the target word. And you're saying that this is a nice general purpose representation that you can use to provide features for other neural networks. Generally speaking, if you have enough, you'll see in the rest of the course, if you have enough training data and vocabulary coverage, it's generally better to just train the embeddings directly on your task. If you're learning a translation model, it's just, you can randomly initialize your word vectors and then learn your English and German vectors based on how well English translates into German. But if you don't have very good vocabulary coverage, if, for example, in your you have a very small amount of training data, then you might benefit from learning your word representations using Word2Vec on a larger amount of unlabeled data. Yeah, I'm just going to end here, actually. Are there any questions? Yes?
I had a question about the German and English sentence.
Yeah.
Because it used Euclidean distances for the sentence vectors.
Mm-hmm.
Could you use the cosine distance you mentioned earlier?
In you mean the German and English task? No, you simply use you want to minimize the distance. Yeah, you could use the cosine measure. Yeah. So this is you could approach. Yeah. So that was just that's an arbitrary choice that they made in their particular model. But you could the same hinge loss, the same max margin objective could be used if you took the cosine between the English and the German sentence and the English and the distractor sentence and wanted to maximize that margin.
Would still work.
Yes. Yeah.
Is there a reason why we should model all words as living in the same space?
Well, you could model different words in different spaces, but I mean the generic idea is that you're going to be the representations you're learning are going to serve as input to a neural network. If you have like the part of speech information, you might want to feed in words based on their part of speech into different Yeah, you could feed those into different parts of a network, for example. I haven't seen anyone do this, so this is an example off the top of my head. In which case, yes, you could represent those with like different length vectors. But typically, if you look at the bag of vectors approach, if the vectors aren't of the same dimensionality, if they're not in the same vector space, then adding them is not a valid operation. And therefore you can't obtain a single representation of your document and you can't classify that. So there is a general purpose to having them all be in the same space because you're jointly learning that feature space alongside with how you use it. Okay. Yes?
Has anyone done adversarial embedding? It seems like a similar task to the hinge loss.
Possibly. I don't think I've come across. Chris Dyer might be a good person to answer this question since he's read a lot more about embeddings than I have in the last few years. Are there any adversarial approaches to embedding learning?
Well, I mean, to the extent that that something like these margin-based approaches are kind of adversarial, you could interpret these in that terms of using some of these adversarial network type architectures, people are just starting to explore applying that to language. And they're usually modeling bigger units than individual words, but you certainly end up with word embeddings as a byproduct of this. The tendency in word embedding research has been more towards how do you get really scalable models on really big data sets, so sort of simpler models, or how do you condition on sort of new kinds of information, like say the multimodal stuff that Ed mentioned, or translations into a second language, or social context, or things like that. And that's where some of the more interesting modeling work comes in. But then, because the focus is more on sort of this new data, people aren't particularly sort of using these very sort of exotic learning objectives. But I think there's some really interesting, there's certainly a paper in there if you want to do that.
Okay, well, thank you very much.